Welcome back to Mass Spec. We've done many functional groups, and today we're going to look at aldehydes, how they can break up in your Mass Spec and get kind of unraveled to give different fragments over here. As we said before, the first peak is typically the molecular ion peak. The molecular weight of this molecule can be gauged from that peak. Now, the highest peak is the one that's typically most stable and is set to 100%, and then the other peaks are estimated relative to that. All right, so let's see what we can do with this aldehyde here. So this is 1, 2, 3, 4, 5 pentanal, and as we said before, the lone pair electrons are the most vulnerable of all of them. So it gets taken out by that electron stream that comes at very high speed and energy. So once you take that off, you are going to get a molecular ion peak that is going to have a radical cation, and that is 86. Molecular weight is 86. Charge is 1, so m over z is 86 for this. It's a very small peak, and right next to that you have an 85. One difference means a proton, right? That's all it can be. And well, we see that proton sitting right here. So right next to this is your alpha, beta, gamma. So you can cleave that bond or cleave this bond, and you will see fragments resulting from that. So let's call that an A. Cleavage right here. And let's see what we get here. So A is when you have the hydrogen then go away with your radical and give you a triple bond. So the hydrogen actually goes away as a radical. So here we go, we have this bond, these two electrons. These hold hands to make a triple bond, and this leaves. So you will have a triple bond here, and we have a lone pair there, and you have the tail and your H going away. So this is a 1, and this is 86 minus a 1 is an 85. And the charge here, if you look at the oxygen, 1, 2, 3, 4, 5. It should have 6 in the periodic table. It's only got 5. So 6 minus 5 is going to be a 1 for the formal charge. So therefore, you have a positive, and the detector can record the positives, and the mass over charge is going to be 85 for that. All right, well, if you can do it on this side, obviously you can do it on the other side. So let's see what happens on the other side here of this molecule. Let's call that a B. So on the B side, you can take the same thing and cleave it so that you get a triple bond here and a radical here. So that's going to go to an HC, 1 lone pair remaining, a triple bond, 1, 2, 3, 4, 5, 6 minus 5 is a +1 charge, and so that is going to be recorded here by the machine. And here you're going to get a 4 carbon fragment here, all right? So you know this is about 57. So you add them up, that should give you an 86. What else do we have? So we know how you got the 29, we know how you got the 85, 57, this is also a 57, which means if you had a heterolytic cleavage here instead of a homolytic cleavage, this side is going to become positive. So that's C, and again, it's going to be on the same place, but it's going to be heterolytic instead of homolytic. That's the only difference. So you take the same molecular ion peak, and instead of just giving 1 electron, you give both over here. And you will see that this is then going to become, well, you put 2 electrons here. There's already a lone pair here and an unpaired electron. And so now you have, this is your new pair of electron that comes over here. You will have 1, 2, 3, 4, 5, 6. So 6 minus 6 is going to be a 0 charge here. This has no charge. So it goes down the chute, and you will not record it. However, this fragment here, which probably can go, this is a primary, you can probably go to a secondary and stabilize. This would be recorded as a mass 57 charge 1 m over z 57 peak, which is what we have. So we pretty much have a good understanding of how this is formed, and this is formed. But the tallest peak here is the 44. Well, we got to address that for sure, because we really haven't talked about this part of the molecule. How can you form a 44? All right, so let's see how we can form a 42 and a 44. When you have a carbonyl, the carbonyl's got a chain or a long tail here wagging around. The tail can kind of flip up, and it can the head can just bite off a hydrogen. And that's what happens, alpha, beta, gamma. So this is also called the McLafferty rearrangement. All right, so here, well, we can use this electron or this electron. It doesn't really matter. This goes over and grabs the hydrogen. And I have to draw all of this at the same time because it's kind of like a concerted process here. We will be doing something like this later on with rearrangements, so you will be seeing this again. So here are the sigma bonds that are going to be broken. I'm drawing out the electrons on that. So then this electron holds hands with this and makes a pi bond right there. So you pretty much kind of chop it right here and get this out. And that's just going to be an alkene. So here, remember, there are two hydrogens here, and so you will have a alkene here, a hydrogen gone, a double bond, and here's your CH3 from that tail. So that is about 42, which means this is going to be 44 because both of them will add up to then 86. Okay, so, and that's the most stable peak, because if you look at this, you have a double bond right here, and that double bond can then have a very nice resonance with all these other electrons. And you still have that lone pair, and so 1, 2, 3, 4, 5, that's a plus. We see that this is going to have a positively charged ion, and you can write, I can write it out here or here, and you can have an OH. Okay, you can see that this can do resonance here by going back and forth. All right, so this is resonance stabilized, which is, how you would get the additional stability. All right, so here you can see that this is going to have, I'm just going to draw resonance stabilized hybrid for that. So typically the tallest peak, it tends to be the most stable as well. Now it says over here you have a little tiny sister peak here right next to the 44, which means that's 2. 44 minus 42 is 2. And obviously for 2, you have to take out 2 of the smallest things out there. Take out 2 hydrogens. Well, how can we do that? So let's look at how we can take off 2 hydrogens. If you take this same molecule, and I'll just do an E here. If you take this out, and you can take out the hydrogens from here, and that would leave you with another new functional group. So here I'm going to just put this out, plus, and you can think of hydrogen just leaving here as hydrogen gas, which is neutral. That's 2, which means you'll have another double bond here. I'm just going to put CH2 here. So this is your CH2 from where you're going to do this. All right, so that is going to give you a CH2 with a double bond here, and then a double bond to oxygen. And that oxygen now has lost its hydrogen, but it's still got a lone pair and an unpaired electron. And to find the formal charge, we can do the same thing. 1, 2, 3, 4, 5. 6 minus 5 is going to be 1. So we will put a positive here, which means it's going to hit the recorder, and the recorder is going to say 42 coming through, make way. And that's how you get the 42 peaks. So there you go. We kind of accounted for pretty much all of them right now. And that's a typical, this is, the alpha cleavage is really very typical. And McLafferty rearrangement is also quite typical of aldehyde fragmentation patterns. All right, in summary, I just want to say that when you have carbonyls, ketones, aldehydes, carboxylic acids, and other carbonyls have a very similar pattern as you would have noticed. They have alpha cleavage, and so you have things that are cleaved after this carbonyl and this alpha between them. And you can also have gamma cleavage or McLafferty rearrangement, and we've seen that a lot. So here, the 44 is your most stable peak. Initially, I had drawn this over here. I just wanted to show you this is also a possibility. This electron can do resonance with this pi bond and, going back and forth. So this is probably the most stable base peak here, the base peak here. And that radical cation is at 44. You lose hydrogens, you can get a ketene. All right, so we'll see a few more, and then you're going to be experts at mass spec. Talk to you soon, guys. Bye.